Chapter 7, Time, Domain, Performance of Control System. Okay, because time is used as an independent variable in most control systems, it is usually of interest to evaluate the state and output responses with respect to the time, or we can say only time response. In the analysis problem, we will use always a reference input signal to the system, and we will evaluate the performance of the system according to this input. Okay, so as a general expression, in most modern system problems, modern control system problems, the final evaluation of the performance of the system is based on the time responses. Maybe we can write this expression. As a general expression, we can say in most modern control system problems, the final evaluation of the performance of the system, of course, is based on time response. Okay. The time response of a control system is usually divided into two parts, as I said before, the transient response and steady state response. For the stable control systems, transient response is defined as the part of the time response that goes to zero as time becomes very large. For the stable control systems, transient response is defined as the part of the time response that goes to zero as time becomes very large. Okay, so we can say for the stable control system, transient response always should be goes to the zero. The steady state response is simply the part of the total response that remains after the transient has died out. So in a general expression, we can write yt, which is output for any system, include the transient response of the system and also steady state response of the system. Ytt denotes the transient response, Ysst denotes the steady state response. For the stable control system, yt should be goes to the zero when t approaches to zero. So we can express it in mathematically. When t approaches to infinity, ytt should be zero. So we can say the steady state response is simply the part of the total response that remains after the transient has died out. Okay. All real stable control systems exhibit transient phenomena to some extent before the steady state is reached. Why? Because we know all real system has some inertia, mass, or inductance that are unavoidable in the physical system. Okay? Because of this, the real system have always inertia, mass, inductance effect. So the transient response in all the system, all physical system. Okay, the response of a typical control system cannot follow sudden change in the input instantaneously, and transients are usually observed. How can we evaluate the control system? First of all, in the real, we will apply the some test inputs to the system. Okay, so we can understand from the behavior of the system which is to be controlled. Transient response is important for us because the deviation between the output response and input or desired response before the steady state is reached must be closely controlled. Steady state response also is important because it indicates where the system output ends up when time becomes large. For example, for a position control system in a DC machine, steady state response when compared with a desired reference position gives an indication on the final accuracy of the system. For example, you want for a speed control 400 RPM from a DC machine, but the final value of the system 380 RPM. So we have a difference here as 20. It is this steady state error for us. So steady state response is also important for the accuracy of the control. To evaluate the performance of the control, we should apply a test signal to the system. Let's start to the test signal now. Test inputs or signals. One of them is usually widely used in the control system is, of course, step function. Okay? Step function. What is the importance of the step function? The step function is very useful. For what? As a test signal, of course. For what? Because its initial instantaneous jump, as you remembered, in amplitude reveals a great deal about a system's quickness in responding to inputs with abrupt, it's important, with abrupt changes. So we can say again, the step function is very useful as a test signal because its initial instantaneous jump in amplitude reveals a great deal about a system's quickness in responding to inputs with abrupt change. Okay, as you know, step function can be expressed as R for t equivalent greater than 0, and we know it's 0 for the time less than 0. Okay, what is the R here? It is the magnitude of the step function. Magnitude of the step function. Okay, as you know, as a step function, we will use in the lecture UT. Okay, UST is the unit step function. We can also show it on the graph as like that. This is the RT signal with respect to the T, of course. The amplitude of it R. So we can say RT is equal to R times UST. Okay, what about the other test signal? The other test signal is ramp function. What is the importance of the ramp function? The ramp function has the ability to test how the system will respond to a signal that changes linearly with time. Okay, it's important. So we should write it maybe. The ramp function has the ability to test how the system would respond to signal. Which signal? Signal is a signal changes linearly with time. How can we express it in mathematically? RT is equal to R times with T times with UST. In here, R is a constant, real constant again. We can express it also in a graph. as like that. This is RT with respect to the t. In here we can say slope will be R, and RT is equal to RT UST. Okay, what is the Laplace domain of the signals for the unit step function? As you know, for the step function we can say Rs will be R over S. Okay, what about the ramp function? For the ramp function we can say Rs will be R over S square in the Laplace domain. The last test signal for comprendo this lecture is the parabolic function. Okay, the parabolic function represents a signal that is one order faster than the ramp function. Okay, its importance of this represents a signal that is one order faster than the ramp function. Mathematically we can express it. Maybe we can write it here again. It represents a signal that is one order faster than ramp function. Okay, we can express it in the mathematically. RT is equal to R times T square over 2 UST. So in the Laplace domain we can say it will be R over S cube. Okay, we can also say this: from step function to parabolic function, the signals become progressively faster with respect to time. Okay, so you have a system and you want to test this system for the abrupt change. So you can apply a test signal as a step function. You have a system and you want to know this, how this system reacts to the linearly changing signal. So you will apply a ramp function to this system. You have a system and it is faster than any system, and you're curious about the response for the faster actions. So you will apply parabolic function. Maybe we can write this expression also: from the step function to parabolic function, the signals become progressively faster with respect to time.